Tau Day, everyone. In case you're not a math geek, tau is the proposed alternative to the constant pi. While pi is defined as the ratio of the circle's circumference to its diameter, tau is the ratio of the circumference to the radius. This means that tau is 2 pi, or about 6.28. Tau is better than pi for a lot of reasons that you can probably find by doing a quick Google search, but we're not going to get into this because this video isn't supposed to be political. Plus, we already know that tau is better. If you're watching this video as a pi conformist, instead of getting angry, you can wait to watch this until Pi Day and then divide everything I say by 2. Oh yeah, I also talk with my hands a lot, so if that's a little annoying, I'm sorry. Alright, to celebrate, we're going to find a way to calculate tau. This is a method that I derived myself, but I doubt I'm the first one to discover it. If you can remember this, then you have the opportunity to impress all of your nerd friends at the local tau party. Here is an arbitrary, regular polygon. It's obviously a hexagon, but just imagine for a moment that you have no idea how many sides it is. This segment here is called the apothem. The apothem is a perpendicular bisector of the side of the polygon with an endpoint at the center. So this is a right angle, and these two segments are congruent. You can think of it as the polygon's radius. If we could find a ratio of the perimeter to the apothem, we can get a decent approximation of tau. With more accuracy, the more sides we have. For future reference, we're going to call the number of sides in our polygon n, the side length s, and the apothem length a. If we draw in this segment right here, we get a right triangle. This angle here has a measure of 180 over n degrees, because it is half of the center angle of the polygon. The tangent of this angle in degrees is equal to the opposite side of the right triangle over the adjacent side of the right triangle, which means that the tangent is 1/2 s over the apothem. We can arrange this equation to isolate s, so we can leave everything in terms of the apothem. Now we have a times tangent 180 over n equals 1/2 s, and then we can multiply out 2 to both sides, and that will give us s equals 2a times the tangent of 180 over n degrees. The perimeter of the polygon is equal to n times s. That is 2na times the tangent of 180 over n. If we divide this by a, we get our approximation for tau. The a's cancel, and we get tau is equal to 2n times the tangent of 180 over n degrees. If we put in a really big number for n, then we'll get a really good approximation for tau. Or more specifically, the limit of this expression as n approaches infinity is equal to tau. So let's try it out. So I've got my scientific calculator here. And remember that it's set to degrees, not radians. We're going to put 2 times, let's say 3 times the tangent of 180 divided by 3. And here we have n equals 3, so we're substituting 3 for n. We get 10.3923. So, somewhat close to tau. 2 times 10 times the tangent of 180 over 10 we get 6.49, so even closer. Let's try 2 times 100. 6.285253. Still closer. 2 times 1000. 6.283205. We can calculate a ton of digits of tau using an online high precision calculator, which is what I'm going to do. So this is just an online high precision calculator that I found on the internet, and I'll put the link in the description. So first, as a benchmark to see how accurate our approximation is, we're going to enter 2 pi. Execute. And we're going to copy this into a Pages document and compare it to the approximation that we get from the expression we derived. Now let's try the expression that we used. So it's let's do 2 times 10 raised to the 500th power times the tangent of 180 over 10 raised to the 500th power. And let's see what we get. It looks like the same answer. And when we paste it onto the Pages document, we can see that it is the same answer, digit for digit. I hope you enjoyed that. Happy Tau Day!